Hello, everyone watching this. I'm Luke Gibson, a fifth-year PhD candidate in Jim Fentner's group at the University of Washington in Seattle. Today, I'm excited to talk about a project that I worked on during my time at Pacific Northwest National Lab under the guidance of Dr. Chris Mundy. Now, as the title of my talk suggests, I'll be talking about how we're constructing a workflow for computing electron transfer rates within a heterogeneous system where we have a model graphite anode reducing liquid electrolyte. And I'll briefly cover Marcus theory and the main quantities that are involved, as well as how we use molecular simulations to compute these parameters. Now, nobody needs to be convinced of the importance of batteries today. They have many applications ranging from small handheld devices to electric vehicles, even up to grid-scale storage. However, these batteries are not without their drawbacks. The most popular battery chemistry on the market right now is lithium-ion battery. And these batteries are extremely powerful due to their large power densities. Here we have a schematic of one with many of the modes of capacity fade shown. And I like this figure because it gives you an idea of the complexity of the processes occurring within a battery. And the common components of the battery are numbered here with example materials. First, we have the anode. On the other end, we have the cathode. Between them, we have the electrolyte, which contains your lithium salt, and your electrolyte solvent, which helps shuttle the ions back and forth between the electrodes. We also have this solid electrolyte interface layer, SEI layer, and I'll come back to this. And lastly, we have the separator, which helps prevent electrical contact between the electrodes. Now, any of these mechanisms can be the topic of a full PhD, but I'm focusing on number 4, the solid electrolyte interface layer, or SEI layer, which is simply just a layer that builds up at the interface of the anode and liquid electrolyte as a result of reductive decomposition. Now, we're looking at this because it's known that this formation of this layer is one of the main causes of capacity fade in batteries, and its growth mechanisms still aren't well understood. Now, if we zoom in to the atomistic level where we have the electrode surface, we could see several processes that are occurring during charging, which are listed here on the right. Here we have a graphite anode surface in contact with liquid ethylene carbonate, a commonly used electrolyte. And only one here is shown for clarity, but we do have a full liquid phase contacting our surface. And so first we could have lithium intercalation, which is just the preferred process where your lithium ions intercalate between the graphite sheets. We could also have an electron hop from the surface onto one of the electrolyte solvent molecules. And if temperatures are low enough and the voltage is high enough, we can even have lithium plating where lithium ion is reduced to lithium metal and deposits on the anode. There's several other processes that can occur during this charging as well. And so this now brings us to the goal of our study. Firstly, we want to construct a workflow that allows us to compute the rates of heterogeneous electron transfer. And a good starting point is to use Marcus theory for that, which lets us use this equation here at the bottom to estimate the rate constant for electron transfer, given a series of parameters. And secondly, we ultimately want to better understand the first step of SEI growth, where the electrolyte is reduced. And in our study, we'll be looking at 3 acceptors: ethylene carbonate, a lithium ion, and a combination where we have ethylene carbonate solvating a lithium ion. But before I get too far, I'm going to briefly explain Marcus theory for anyone who's unfamiliar. So in Marcus theory, we ultimately construct 2 parabolas that portray the free energy profile along some reaction coordinate, which we'll see is largely a solvent orientation coordinate. Now, if you have these parabolas fully defined, you can ultimately compute your rate of electron transfer. But there's a lot of nuance to these parabolas, and I'll go through how their shape and locations affect the calculation. First we have the gray curve here, which denotes the reactant state, in which the charge is localized on the donor species, which we see here on the left. We see that the solvent orients appropriately due to this localization around both the donor and the acceptor. But on the other side, in the product state, we have this gold curve, in which in this basin right here, we have the charge localized on the acceptor, and the solvent has reoriented in response. Now, you could imagine that if we have our reactant state and just freeze all atomic coordinates, but transfer over the charge via this vertical excitation, we would be hopping over to the product curve, but the same reaction coordinate, which would yield a much larger energy. And that would just look like this, where the solvent has not reoriented, but the charge has transferred. And so this helps us orient ourselves when looking at these curves and to help us understand what each point represents. So going back to Marcus's equation, we see that there's 3 parameters that we need to compute in order to calculate the rate. And each of those quantities are depicted in the plot on the right. First, there's the electronic coupling, VAB, which is a quantum mechanical parameter that describes the overlap between the reactant and product states. And an important aspect to understand is that if this coupling is large enough, these curves reform to produce 2 adiabatic states, where your gray curve is your ground state, and the gold is your excited state. The second is the reorganization energy, or lambda, which is quite literally the energy of relaxation after we freeze the atoms in the reactant basin and transfer that charge and let the system relax, which is just shown by this lambda arrow here. And this quantity is governed by the horizontal distance between the 2 parabolas. How far away are they on the x-axis? And lastly, we have the free energy of reaction, which is pretty straightforward on the plot. It's just the vertical offset between the 2 parabolas. Now that you're up to speed with the aspects of Marcus theory, I'll quickly cover a study from Elon Benjamin's group that inspired a lot of our work. Now, in this study, Rose and Benjamin looked at electron transfer from an electrode here to an iron 3 ion in water, which are denoted by these gray arrows. And on the left, we see the Marcus parabolas that they constructed, where the x-axis is the electric potential on the acceptor species. And this U0 term here is just a constant shift that forces the crossing point to occur at 0, right here. This iron ion is strongly coordinated with 6 waters, which are denoted by these lighter gray arrows. However, once we transfer the electron, we see this change in solvent structure, going from the iron 3 to iron 2. And since the ion is becoming less negative, we see a loosening of the solvent shell, but it's still strongly hexacoordinated. So this shows us that even small, subtle changes in the solvation environment can lead to large changes in the energetics of our system. And so we see that each of these 3 parameters need to be calculated in order to compute our rate, and I'll go over how we plan on computing each of these quantities. I'll first start with the electronic coupling. Now, as I described earlier, this coupling parameter is a quantum mechanical value that describes the overlap you have between the orbitals from your donor and acceptor species. Now, there's not enough time to fully describe the process, but we plan on using the projector operator-based diapetization method to compute these couplings, which lets us define donor and acceptor regions in your system and compute the couplings between them. We plan to evaluate also the configurational dependence of this coupling parameter for each of the acceptors in our system. So we're going to look at distance from the electrode as well as the orientation of them at the interface. The next parameter is the reorganization energy. On the right, we have the Marcus parabolas for ethylene carbonate at the electrode interface, with the x-axis being the same reaction coordinate that was used in Elon Benjamin's work that I described earlier, which is just the electric potential on the atoms in the ethylene carbonate. And so to construct this curve, we couldn't simply just sample the configurations in each parabola or each state, because we'd only explore the areas immediately near the minima. We wouldn't be able to reproduce the full curve. So in order to produce the full curve, we employed an enhanced sampling technique known as umbrella sampling. which lets us run simulations in multiple regions along the x-axis and back calculate the true curve. And we did that here by actually changing the ethylene carbonate net charge from 0 to -1 by quarter charge increments. And so this plot tells us that the reorganization energy for ethylene carbonate at the electrode surface is approximately 38 kcal per mole, which is quite sizable and can't be ignored. Lastly, we have the free energy of reaction, which is a much more involved quantity to compute. And we see in equation 1 here that this free energy is comprised of two energies. The first is the change in the free energy of solvation, and the second is the change in intrinsic energy. Now, this intrinsic energy is defined below in equation 2, where we have this delta E naught, which is just your difference in electronic states, electronic energy levels, rather, which includes your electron affinity of your acceptor and your ionization potential of your donor. But we also have the second term, which is this overpotential term, which has an external bias that raises your Fermi level, which ultimately affects your free energy of reaction. And then we have this third equation, which describes your change in solvation free energy. Now, there's not enough time to go into the full detail about how this is calculated, but I'd be happy to talk further during the live Q&A session about this. But its result is shown here on the right. We have the solvation free energy on the y-axis and the species charge on the x-axis. And as I said earlier, we're looking at 3 acceptors, each of which are shown here. However, by the nature of the calculation, we computed the charging of a lithium atom to a lithium ion, which is shown in this blue reaction. Which is actually the reverse reaction of what we're interested in. So the blue number here shown will actually be inverted to give a change in solvation free energy of positive 106.7 kcal per mole, while the other 2 quantities do remain negative. And so the overall trend we see is shown here at the bottom. The solvation shell ethylene carbonate has the most negative change in solvation free energy, whereas lithium ion reduction is largely positive. And so this, in conjunction with the intrinsic energy changes from equation 2, suggests that ethylene carbonate in the solvation shell of lithium ion is likely the most favorable. Now, after a few assumptions, we can preliminarily compute these rates of electron transfer and look at the trends of the 3 systems. On the right, we have this plot where the y-axis is the natural log of the computed rate constant, and the overpotential that I mentioned earlier is along the x-axis. Now, I should note that this overpotential is not yet aligned to a particular reference electrode, however. But given this information and that these are preliminary results, the exact quantities are less important. I want to focus more on the trends between the systems. And in this, we see that for a range of overpotentials, the solvation shell ethylene carbonate has a significantly faster rate of electron transfer, which is just this orange curve. However, after a certain voltage is reached, we see that the liquid ethylene carbonate overtakes the solvation shell ethylene carbonate, which is due to this inverted region, where an increase in the driving force or free energy of reaction counterintuitively decreases the rate of electron transfer. And this is known to occur experimentally as well. The lithium ion is not even shown here in this plot because it has an extremely small rate constant, which qualitatively makes sense. Now, while these models do have a lot of simplifications and are ideal scenarios, it's an important first step towards addressing a notoriously difficult problem in theoretical settings. So the next steps in this process, or this work, is to finish computing the electronic couplings and reorganization energies, and then construct a generalized Langevin equation to better estimate these rates, since we could then account for explicit solvent fluctuations, particularly in the transition state region. Finally, I would like to thank my research group and, of course, my PI, Jim Fentner. I would also like to thank Chris Mundy and Sam Johnson for their helpful guidance and discussions throughout my time at PNNL, as well as all my funding sources and computing resources at UW and PNNL. So that's the end of my talk. Thank you for listening. I'll be happy to answer any questions during the live Q&A session on Thursday morning at 8 a.m. Pacific Standard Time. Thank you.